Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thank you very much for coming. I apologize for being slightly late. We were rushing and no excuse, but sorry. Anyway, I'm delighted to introduce Tijana to you. She is visiting us from UCSD. She finished her PhD from Stanford University in 2001 and her BS and Master's from Arizona University. Her interests really are in power consumption, low power consumption devices and techniques for that, and wireless networks, etc. And our bio is, you've already seen that, so I wouldn't go through that. But today you're going to talk about some of the resource management work you've been doing.
Yeah,
so
thanks.
yours.
Thanks. So today I'll talk about resource management of heterogeneous wireless networks. This work actually is an extension on some of the stuff I did when I was at HP Labs. Back there, we actually focused mostly on managing multimedia traffic. So it's a bit of a generalization because the wireless network I'll show you actually has media, but also it has a lot of other types of data present in it. This work is supported by NSF and by a couple other companies. So mobile communication, today already, we have many different types of wireless connectivity. In fact, we have single devices that usually have more than one wireless connectivity. So if you look at your fancy cell phone, smart PDAs, you'll usually have 802.11 chip. You may have Bluetooth. Some will have also infrared in addition to your cell phone network connectivity. So the question is, how do we use this efficiently? And typically the issues that come up with that are, how do you do quality of service for applications that care about it? The things are like voice over IP, watching video. In case of our sensor data, some of the sensor data is quite sensitive to delay and to the amount of throughput that they have, and I'll show you examples of that. The other big issue that comes up, as soon as you have wireless connectivity, you typically like to have a battery as well. The problem is that those two tend to not work too well together, so wireless uses up often a lot of the battery power. So how do we design systems that communicate effectively, that can meet quality of service requirements while at the same time minimizing the energy consumption so your battery lasts as long as possible? And the last big issue that's come up is security. So in my talk today, I'll be focusing primarily on these first two issues. How do we balance QoS and battery capacity? There are actually a couple of groups at UCSD that specifically work on security. So if you have any questions about that, I would refer you to my colleagues there. The wireless network that I'm working with is called HPWREN. It stands for High Performance Wireless Research and Educational Network. This network spans about 100 miles inland. So here's UCSD. It's this little dot on the network. About 100 miles out is Salton Sea. We have some of the sites that span about that far inland. We also have about 70 miles out into the ocean. We actually have wireless connectivity on a couple of research vessels and on a couple of islands. They're off the coast of San Diego. If you look south, we have San Diego State University, and then there's a site that's just by Mexican border right now. We're actually in discussion with researchers in Mexico, in Tijuana, on deploying over there as well. And then up north, it goes to about almost 100 miles north of UCSD. The sites up there are actually at Native American reservations, and they support all the educational needs of Native American tribes in that area. This particular map represents only the top level of the network. So these are the high-speed point-to-point links that we have. You can think of this as a wireless mesh that's set up. The point-to-point links are big, huge antennas that sit usually on mountaintops. Normally, these links are powered. They have line power from the mountaintop locations. A few situations, actually, we had to use solar cells. Those situations are primarily up here on native reservations where there was no power available. So in that case, you would see big, gigantic solar cell installations, like tens of large solar cells normally. Just beneath every single one of these dots sit a layer of sensor node cluster heads. The cluster heads typically run processors that are at the level of a strong arm or X-scale computing, so about 200 to 600 megahertz at most. They usually have a little bit faster wireless connectivity, so something like 802.11. And their job is typically to gather the data from many different sensor nodes. They're beneath them, in some cases to do some data analysis, and then to forward the data to appropriate locations. Now, when I say forward the data, there is not a single sink in this network. So there's not one location that all the data goes to. We actually have many different researchers and many different people who use this network. So there are multiple sinks for data that are present. So just as an example, these two dots that are next to each other represent Santa Margarita Ecological Reserve. Beneath those two dots sit about 80 sensor node cluster heads. They're connected with wireless LAN. And beneath them sit hundreds of sensor nodes. Here are some examples. We have earthquake sensors. This picture is of earthquake sensors that are in the desert. These particular sensors are very high fidelity. So the people who use them are people who work on seismic research. And they're, in fact, on the photo right here. They work at Scripps Ocean Institute. And the reason why you see this big, fat solar cell is because their sensor nodes are fairly large size, very large fidelity, and need some significant data processing capability next to them. So these are not tiny little modes. And in fact, one of the challenges that we have is how do we design these kinds of sites in such a way that you don't need big, huge solar cell and a big, huge car-sized battery to run them, but at the same time still deliver the level of fidelity that the researchers and other people in the field need. Okay? The thing to note here is the amount of traffic. It's very small. Our seismic friends tell us it's 10 kilobits per second. Reality shows that it's about 4 kilobits per second. We have not seen much more than 4 kilobits per second. The problem that we have is it's 4 kilobits per second, but if there is an interesting event, they have to know about it very quickly. Interesting event would be an earthquake, right? So if there's a large magnitude earthquake, from the furthest point that we have sensor located at to UCSD is 4 seconds until the earthquake hits. So obviously you want to know sooner than 4 seconds. And the challenge associated with that is, if this was all a wired network, 4 seconds is not a big deal. I mean, a split second is pretty much what you would expect. But it's not a wired network. This network has a number of different types of wireless connectivity that all have to talk to each other and all have to deliver on the quality of service. And it's not only seismic nodes. It's a whole bunch of other nodes that are also using it. So how do we deliver on this tight delay requirement without necessarily causing problems to the rest of the users? Here's an example of the type of data. This was a very small earthquake, 1.6 in Riverside County. And basically, from their perspective, you can see spectrum analysis. So what they do is they collect the data, run a bunch of algorithms, and then try to detect some anomaly in the data. So if you see lots of black, not much is happening. If you start seeing lots of snow, then some interesting things might be happening. 1.6 earthquake is not much, but it may actually be an event that leads to something much bigger. So how do you detect anomalies that lead to bigger earthquakes? How do you follow on those events? That's actually part of the research that people who use our network do. On the other end of extreme, we have Palomar Observatory. This is an observatory that was recently credited with discovering the 10th planet. And partly why they were able to do that is because they had the wireless connectivity that enabled them to stream the data, detect that something interesting was on the night sky, and then notify people on the other side of the Earth to continue watching the sky at that particular location. So they were actually very pleased with the ability to use this wireless connectivity. For us, the problem is right here. They want to stream 150 megabits per second continually at nighttime. During the day, it's great. So if your earthquakes can be scheduled at daytime, our life is really good. If they happen at nighttime, we have a problem. How are we going to actually balance Palomar Observatory with 4 kilobit per second stream that is trying to arrive there in a split second? When it comes to a little bit more mobile installations, I mentioned to you that we have a couple of research vessels. They're off the coast that are outfitted with wireless connectivity right on top of the research vessel. Each one of them have a number of projects that are going on. So here's an example of a video camera that was used on a submarine, on the submergence unit vessel. So the idea there is you have a researcher that's sitting at UCSD and Marine Institute that basically wants to see what's going on under the ocean. So the video is being streamed from this device up to the top of the vessel and then into UCSD, to his office, where he basically looks for any interesting things that are happening. On the other side, we've worked quite a bit with California Fire Department. So they got all excited when they found out there's wireless connectivity throughout San Diego County. And they said, great, can we use it? So we tried it, and it's actually proven to be very successful. Again, the problem is, for them, using it means only when there's a fire. But when there is a fire, they really need it. They need real-time video. They need real-time sensing data, things like temperature, wind speed, your very basic sensors. They also need just some basic data connectivity, email, messaging. How do you tell your troops somewhere in the field where to go? That's basically what they've done using our network. So here are a couple of examples. This was when fighting an eagle fire in May 2004. We actually deployed a couple of antennas. These antennas talk to our big wireless mesh in the backbone. And they were used to stream a bunch of sensor data and also a bunch of communication messages between various command posts. Here's another example when we actually used video on a helicopter. And this video data was streamed to the mountaintops. And then from there into the hands of people who were deployed in the field. And what they were trying to do is see how the fire is spreading so that they know how to fight it. So here are some examples. These are daytime examples. Here's an example of nighttime of what they might see. Yeah?
So how reliable is the setup? Is there a different mechanism that can be used to communicate with these people, like satellite?
So fire department normally relies on telephone company. A telephone company typically comes in and drops a line wherever they need the connectivity. And in a lot of cases, it works really well. But in actually a number of cases, it takes significant amount of time to get the connectivity in. So in the case of this particular fire, the September 2005, this was about 30 miles north of where my house is in San Diego. It took 2 days for the telephone company to drop a wire into the command post. It took us about an hour to set up connectivity. So after that experience, the San Diego Fire Department basically said, look, we need to have something like this kind of connectivity.
Why not cellular?
Because cellular doesn't reach in a lot of these areas.
You could set up a temporary cellular station on a LAN, for example.
Sure, if you have the money to buy the base station. Yeah. Yeah, the difference is in cost, obviously, right? You have to have an agreement with a cellular provider. You have to have the money to buy whatever station that you have to set up. But then it would work great, I agree. In our case, this is a very simple wireless LAN connection, that just has a fat antenna on it. So it's very cheap and very easy to deploy. Yeah. And that's really what was attractive, I think, because it provides enough of connectivity. It's faster, obviously, than Zigbee would be, but it's also cheap enough and small enough, and very easily deployable. So here's some examples of research going on in Santa Margarita Reserve that I had mentioned to you. This is a student that does ecology research on the reserve. You can see she has her laptop and then has a big directional antenna connected to it. She's using 802.11 card with a directional antenna to get to the data in her sensor network, and is sitting up on a mountaintop, watching for wildlife. Down here is an example of a sensor equipment setup. You can see that these things are not very small, and that is, again, because they need very high fidelity, and they oftentimes need enough processing on those sensors. So I would say, the area that we're working in is quite a different area than what you normally read about in sensor networking literature. Here's an example of motion detect cameras. Those are used to watch wolf behavior at California Wolf Center. So you can see that we detected some wolves in the movement. Obviously, motion detect cameras can detect other things as well. So these are a couple of examples of that.
So I have a
Yeah.
generic question. For sort of life-critical things like fire and some medical emergency and all, is there any particular reason to constrain yourselves to dot 11 or any of the SSC constraints in the power that you can use for transmission? Can't you just say there's an emergency situation where you can just blast, not go 1 watt, but go multiple watts on that?
Yeah, Yeah, you can certainly do it. I think the real constraint that ends up being is more in terms of energy. Because if you're deploying around the perimeter of a fire, you usually don't have a plug readily available. So it kind of depends. If you're right next to a truck that can provide the energy, no problem. If you're not, then you may want to think about it. Which is why I think this kind of hierarchical organization is a very good way to do it. Because you can bring in relatively powerful connectivity very close, to where you need to be, and then you can actually stream at lower level the rest of the way. So here are examples of acoustic sensors. The researcher is actually trying to detect wolf behavior. So they're trying to watch for both sounds, the types of howls that wolf produces, and coordinate that with the physical movement that you see on the wolves using these motion detect cameras. So in this particular case, you can see wolf howling, and you can see the specific pattern of howls. So to a researcher who knows more about wolves, this would tell him something. To me, obviously, it doesn't say much other than you see pretty waves in the picture. And I guess what I'm trying to illustrate here is, in the case of acoustic sensors and video motion detect cameras, there are specific events that they need to trigger on. When those events happen, you want high fidelity data to be available. Huge percentage of time, you don't really care. Nothing is going on. So there'll be moments when QoS is important, and a lot of other time when it's not. You need to be able to adapt. Some of the basic sensors, these are Mount Laguna sensors. These are primarily things like rain gauges, wind speed measures, and similar, relatively simple sensors. So these are things where you don't need as high fidelity, although they look much bigger than what you would expect on a mount. And that is because people who actually give weather reports use these. Just to give you some illustrations, the types of wind gusts that we measure on Mount Laguna go almost as high as 150 miles per hour. So think about putting an antenna on a mountaintop that has winds of over 100 miles an hour frequently. What does that mean to your wireless connectivity and your antenna surviving? So we've had situations where whole parts of wireless link die because the wind was blowing too hard or it snowed too much, and there was just too much buildup of ice. So it couldn't communicate. So you actually have to send somebody out to fix it. This is an example of real-time database alerts that California Fire...
So have you developed something to fix that, or you just live with it?
Yeah, we've lived with it. But I think our conversation on how to do network management is a big issue on this kind of a network. First, usually when there's a big event like that, the whole tower goes down, it's pretty easy to detect where it happened, because data just doesn't come through over there. But if you think about a gigantic network, so if instead of just 100 by 100 miles square, this was all of United States, you really wouldn't want to go out and try to figure out which one of the millions of towers went down. You'd like somebody to tell you the problem is here. And this is what the problem is, right? So real-time database alerts. This is for California Fire Department. The idea is you have all these weather sensors placed on all kinds of critical locations throughout the county. So can you actually trigger an alert when something of interest happens? So if you have low humidity, high temperature, a lot of wind, that would mean that chances for fire are pretty reasonable. So at that point, there would be an alert sent through either email or pager or cell phone or all of the above to somebody responsible in California Fire Department that says, look, you should watch at this area. At that point, they might actually they have special cameras that can scan for smoke, that we have placed in a couple of critical locations. So at that point, they may enable that camera, do a quick scan, say, okay, is there anything going on? Nothing is going on, life goes on as usual. So to summarize, we have data acquisition part of the network, which is a whole bunch of different sensors. These sensors, some of them are very time sensitive, like seismic nodes. Some of them really don't care. Temperature you can measure every 15 minutes to an hour, and it doesn't matter, plus minus 5 minutes. On the bottom, I'm showing a data distribution network. What I mean by data distribution is how do you get to this data you have just measured? What do you use? So you saw a student with a laptop in the field. We have people who take their iPads, their PDAs, their even cell phones have been used. And then on the other end, we have incident command posts. So this is a laptop sitting in a truck. Or we have people that are completely on the back end. So researchers, at UCSD, at San Diego State University, in some research posts that we have along the network. And finally, we have collaboration with people in San Diego Supercomputing Center. So if you, a lot of these data actually cannot be immediately analyzed, so they store it for later analysis. And then the question is, can you actually design some interesting database techniques that can help you detect where the interesting behavior is and when that behavior happened in a particular sensing stream? So this is research that's actually happening now in San Diego Supercomputing Center. So our network can be characterized by 3 levels. The top level is that map I showed you. It's the wireless mesh backbone, big, huge antennas that provide reasonably fast speed. There are typically no problems with battery lifetime there. We're line powered. We do have an issue with QoS scheduling and routing at the top level. That issue is right now addressed by routers. So we basically programmed routers to use some very basic packet QoS methodologies. On the middle level, we have sensor node cluster heads. Cluster heads, as I said, are at the level of about strong arm X-scale processing power. They usually take the data from a bunch of sensors. They may do some data processing and analysis, and then they'll forward the data to whatever location is needed. So they don't necessarily follow, will send the data just up in the hierarchy. If a researcher is sitting right here, cluster head will stream the data directly to the researcher. At this level, there are 2 issues we're dealing with. One issue is the quality of service for the particular applications that need it. The other issue is battery lifetime. So at this level, we have reasonably small size nodes that are powered by solar cell coupled usually with a battery that's right now fairly large size. The reason why we're worried about battery right now at this level is we would like for this to be much cheaper to deploy in the future. So if you do the research on reasonably small scale, you can afford to spend money on a big fat battery and a huge solar cell. But if you really want this to be a real thing, that people in industry and in other fields will buy and use, it needs to be cheap enough and easily deployable. So in order for that to be the case, we have to save power. So this is actually an area that a lot of our research is focused on right now. At the lowest level is a sensor network, which is a bunch of different sensor nodes. They have different characteristics. I showed you just a small sampling of them. They have different types of connectivity. So some will use Zigbee-like connectivity. Some are actually just even wire connected. There's a huge variation on what is available here, which I think is very characteristic of what you would expect in a real deployment. Typically people don't sit back and say, okay, I'm going to design my whole network and that's how it's going to be forever. You design it, you deploy it, and then you keep adding to it. And as you add to it, things change. At this level, we do have big problem with battery lifetime. The smaller the node, the more battery issues you have. There's also some problems with quality of service. So if my seismic node at the bottom here doesn't have any concept of quality of service, it makes it impossible for me to guarantee QoS at the levels above it. It needs to know, and it needs to have a way to communicate to me that it has some limitations. So if you look at sensor network literature that's been published in recent times, there has been very little that people have addressed in terms of QoS. Most of the work really focuses on how do you make the network survive long enough to give you the data. What we're interested in is not just survival, but also how do you deliver the data that is sensitive in time or is sensitive to bandwidth. So our initial testbed is Santa Margarita Ecological Reserve. What makes this particular testbed nice is it happens to have 80 sensor node cluster heads connected with wireless LAN. It also has very interesting topography. So there's a big canyon, that Santa Margarita River that runs through it, that also has a number of mountaintops and some level fields. So that provides us for a very easy way to study how would one deploy realistically such networks. Secondly, it represents just about every type of sensor we find except for a few. So we don't have an observatory on there, but we have almost everything else. And the people with Santa Margarita Reserve are pretty desperate for some level of implementation of quality of service coupled with minimizing power. They don't have huge amounts of money to buy big solar cells, and they would like to be able to guarantee some quality of service to their data. So they've been very open to working with us. So at sort of a very high level, the way you can think about resource management, that's what this RM stands for. What you have is something that produces data. The data gets buffered up in some sort of a queue or buffer. And then at some point, it determines how you're going to use the resource you're talking about. That resource can be wireless connectivity. It may be processing power. It may be your storage. The resource can be either active, so it can be doing something to the data, sending it, processing it, storing it. It may be idle, just sitting there waiting. Or it may actually be in some low power state. So the question at the device level is, how do you control what state it's in, and how can you predict what is it that you should be doing next? And if you can predict reasonably accurately, you can save a lot of power and deliver really well on quality of service. So if we look at power issues specifically, on sensor nodes, almost all of the power will go to radio. Very little goes to sensors, and very little goes to CPU. Now, the CPU part is a little bit misleading because this particular graph shows a very small sensor node. For anything larger than very small sensor node, you're going to have a larger percentage of power going to CPU. On the bottom, I'm showing you a breakdown for something that's much like a cluster head that has strong arm processor coupled with wireless LAN. And we're showing energy breakdown for voice and for video. And you can see on voice that basically almost all of the power really goes to radio. Relatively little goes to processing. For video, it shows it at half-half, but notice why. You have encode going on for video. Have any of you tried doing encoding on a strong arm processor of video? If you have, you know why this is a problem. So strong arm is not designed to encode video. It doesn't have a concept of floating point numbers in the first place. So basically what you're doing here is emulating. And that's why this is taking so much power. In reality, what you do for encode is you'd put a DSP on the device, and then this picture would look a lot more like this picture here. Okay? So key takeaway is radio is a lot. Processing is probably the second largest taker of power. On 802.11 specifically, people usually tell me, well, that's easy. Just enable the DOS mode. So this is a standard power management mode that essentially listens for the traffic every 100 milliseconds. If there is some traffic to it, it'll listen and it'll communicate. If there is no traffic, it goes to sleep, which really sounds great, except that in practice we found it doesn't always work. So here are the measurements we did. These measurements were done at HP with my collaborators at Stanford and at Italy. So we had light traffic conditions. This is Stanford in summertime right here. Then we have medium traffic conditions. That was HP in summertime. And then we have very heavy traffic conditions, and that was University of Bologna in summertime. So Italians like to talk. And you can see what happens. So what I mean by heavy traffic is there is a lot of broadcast traffic that's on the network for whatever reason. And in heavy traffic conditions, you almost never make it to sleep. You're continually awake. Because every time you get this packet, you need to see whether it's meant for you or for somebody else. And by the time you figure that out, your 100 millisecond window has passed. Because most of the figuring out happens in software, unfortunately. So, it really pays to measure exactly how something is implemented and to not just assume that it's going to work as advertised. The other issue is the issue of contention, which tends to be a problem for us in terms of quality of service. So why contention is an issue? I mentioned to you I have 80 sensor node cluster heads on a single dot. What if all those 80 try to talk at the same time? They're going to be running into each other left and right. And in addition to that, under those 80, there is a whole bunch of sensor nodes. They're also going to have a problem of contending. So every time there's a collision, they'll back off. The more they back off, the more delay I have, the lower the bandwidth I have. So a problem. Now, obviously, you'll see implicit in all this is that everybody's continually awake listening, right? Which is not what I want in terms of power. So these two problems put together actually motivated part of our solution. Because in terms of power consumption, we want the devices to not be awake. In terms of contention, you also don't want them to be awake. You don't want them to be trying to talk at the same time. It's only for quality of service that you actually want it to communicate, but only when needed, right? So that's where scheduling becomes really important. In fact, if you plot the number of nodes versus throughput for 802.11, you see a pretty significant drop in terms of throughput. So the lower the throughput, the less ability you have to meet the delay requirement. So data scheduling, the way we looked at it is we have a couple of different levels where the scheduling could be implemented. A lot of people have looked at changing the MAC layer implementation, which I think is a great way to do it, unless you happen to be at the end that buys hardware. If you buy hardware off the shelf, you can't change the MAC layer. And most of the users out in the field buy hardware off the shelf. So this is why we actually looked at level that's set right between user and kernel space, because that's something that's very easy to deploy. It also happens to be a level where a lot of applications have to talk through. So it's very easy to put hooks into your scheduler that basically tell you this is what my QoS is. The second thing is I mentioned security at the beginning of the talk. So I don't know how many of you work with security, but when I worked at HP Labs, a lot of the security stuff was actually implemented at proxy layer, where you essentially had to authenticate yourself, and then after you were authenticated, you could start the encryption. Now, the encryption may happen in hardware, it may happen in software, it depends who did it and how they did it and when they did it, but invariably, you will have something like a proxy present, which made this level for us particularly suitable to implement scheduling as well. So that is what we did. And the idea was, between two different cluster heads, we want to have a burst of data sent, and then we wanted them to just be quiet, sleep. And then again, another burst of data. Notice these bursts of data are not unidirectional. They can be bidirectional. So at a little more detailed level, what we have is two different applications. They're communicating with each other using whatever method they use normally. So in case of seismic data, what they actually have is they use typical UDP connectivity, but above it, they have an overlay. That's a lot like overlay that people use in videos. They essentially use something that's a lot like RTP to communicate control packets and to make decisions on what they're going to do with data. Are they going to do some pre-processing, or are they going to just stream it? These applications can communicate to my resource manager, which is sitting, as I showed you, right at the interface between kernel and user space. What that allows me is to actually do some very low-level control of power. So I can control device drivers. I can make calls into them. An example was some of the work we did with ACPI on laptops. You can do similar stuff on CE-type devices. The goal here is to basically tell it to go to sleep when you need to, and to wake it up when you need to. Secondly, we did some dynamic clock speed setting. I will not be talking about these algorithms, but I can show you if you're interested. And lastly, we were controlling CPUs, idle and sleep mode as well. So all of that has been implemented. The algorithm has a number of parts to it. First, we need to estimate. So in order to schedule, you need to know what is coming to you, when it's coming, and what are its needs, right? In some cases, the needs will be told. So seismic guys have the overlay. They tell us through their overlay call, well, this is what my QoS is. In some cases, you don't know. In that case, you really just have to estimate and do your best. Based on the estimation of incoming data rates and of the speed that you can process, we can figure out what kind of buffer sizes do we need, how much data needs to be buffered before it can be sent. Then we can figure out the amount of energy that's going to be used. And here what I'm showing actually is both calculation for communication energy. So this would be an example of 802.11. But we also looked at what if I have more than one type of connectivity, so if I can switch between them. When is it suitable for me to choose to switch? And lastly, the policy. What do I do? When do I go to sleep? What type of sleep state? What speed do I process at? That policy actually also needs to be designed and implemented. So some of the characterization we did, this is just a very simple graph of two different traces that basically show the same behavior. This is a plot of the tail distribution of inter-arrival times. If you plot for just World Wide Web calls versus for just Telnet calls. And the reason why I separated those two out is to really illustrate to you that for relatively different types of applications, the plot actually looks very similar. Parameters are a bit different, but the actual design of the plot is almost the same. The key to notice here is this kind of purple line is actually an exponential distribution fit to the inter-arrival times. The reason why I put exponential is most people, when they do quality of service analysis, they use Markov chains. So you can figure out what's your buffer size and what kind of delay, right? So Poisson assumption is typical. It turns out if you have very fast inter-arrival times, your exponential model will hold pretty well. If you have relatively slow inter-arrival times, and these are the times that are of interest to us during idle time, right? Because that's the amount of time that you have to go to sleep. If you have time that's around a second, you have plenty of time to get into sleep and out. Turns out for those, actually you see very heavy-tailed behavior. So you see something that looks a lot more like a Pareto distribution. And yellow line is a Pareto fit. And I'll show you later also sensor data measurements that look exactly like this. So what we said is for our data estimation, we really needed to estimate two things. In active state, so when inter-arrival times are very short, we can use exponential estimation to figure out the rate. In idle time, so when inter-arrival times are reasonably long, we actually have to go with something that's heavy-tailed. That's Pareto. So there are two different types of estimators we use. For the exponential estimator, we use maximum likelihood. Maximum likelihood equation looks ugly, but it's actually fairly simple. What it does is it says I have some rate that my data was coming in at. So imagine video. It was coming in at 15 frames a second. And that was my old rate. In a recent time, I've measured some other inter-arrival times. These are these TJs. Those TJs may map onto some new inter-arrival rate, 30 frames a second. I want to compare the new inter-arrival rate to the old one and see what's the likelihood that actually my rate has changed. That likelihood is this particular part of the equation. If the likelihood is high enough, then I can assume that we have a new rate. If the likelihood is low enough, then I stay with the old rate. And basically, I do this comparison for a set of rates. The calculation actually happens very quickly because basically for each data point, all you have to do is just update the summation and then do a couple of multiplications. That's it. On the Pareto side, what we do is we also use a log plot because Pareto is actually a straight line if you do a log plot. And then we just do simple least square estimate. So just to give you a comparison for exponential estimation, using maximum likelihood, you can see that we actually have very accurate estimate. The ideal is what exactly happened. So in this case, we went from 15 frames to 60 frames of some data per second. The maximum likelihood detected the change exactly with a slight time delay. The time delay is needed because that's how long it takes you to figure out that something actually happened. You need some number of points to figure it out. The other two, exponential averages with different gain parameters, are what people typically use. So they use just a simple moving average. And you can see that you see a lot of oscillations, which basically in our case means is that we'll be fairly inaccurate in figuring out how much data we need to buffer up and how much data we need to send. For Pareto, as I said, we used least squares. And you can see that the estimate for A and for B parameter where something changed is again fairly accurate. And in fact, if we plot an error, you can see that the error is well below 10% as soon as you get beyond about first 1,000 samples. So it's a very quick and very accurate way to estimate. So all of this, maximum likelihood can be used to figure out what size buffering do we need during the time that we're active. What do we need? We need some amount of buffer that's going to be there that we can play off of, essentially, while the device is asleep, and also while it's going in and out of its inactive transition. In addition, we usually add a little bit of cushion because our estimation is never 100% accurate. So that way, we can get real-time behavior without necessarily actually communicating in real time. And this last part is something that we had used on a couple of devices that have more than one type of connectivity. So when it was appropriate, we're able to switch from wireless LAN to Zigbee, or we actually played a bit with cell phone connectivity as well. But in order to do that, you also have to have some buffering available. So based on that, you can figure out the total amount of energy that's going to be used for communication. That's the energy used in the active state, which would be the amount of time you're actually transferring the data plus some cushion time. Then the energy that takes you to transition between active and idle, the amount of energy in sleep, and then any energy you may have used during the switch. And the switch would basically involve having one wireless interface on and having that turned off while you turn something else on. Now, the last part of it was policy. So on a device, if you know about how much data, you need to know also when the next request may be coming in. To predict that next request, you can either use simple predictors or you can actually use an optimal mechanism, which is what we designed. So for each device, you can describe it with a number of states. I have here a few active states. So imagine an X-scale processor that has 4 different levels of processing speed. Idle state, in case of X-scale, it would actually have 4 different idle states as well. Transition to sleep, these are just the times that it takes you to get into sleep and the energy that it takes. And then I have 1 sleep state drawn here, but you can have any number of them. As I said, in the active state, we use exponential model. In the idle state, we use Pareto model. And we actually used renewal modeling theory to figure out what is the optimal policy. So when do we go to sleep and when do we need to wake up? So for renewal model, we have 2 different times we define. One is the time that it takes you to go from active state into idle and back. That's basically 1 cycle of life, you can imagine, in our system. The other possible cycle that we have is the cycle if you go from active to idle. In idle state, you decide, OK, I actually have time to go to sleep. You get to sleep, and then you wake back up. So this second sleep state, S comma Q, basically signifies that you've gotten some request. Q means that there is something waiting in the buffer. So with that, we can define a number of different transitions or different states that we can be in. They're characterized first by a constant, Ci. This constant, in case of power estimation, would be just the power consumption in that particular state or during that particular transition. Then we have the expected time that we sit in that state, plus the probability that first request arrives either before or after you chose to go to sleep. So for example, if we're sitting in the idle state and we want to estimate energy consumed in the idle state, the Ci would be energy consumption in idle, amount of time you spent in the idle state given that your first request came before you went to sleep. So that first cycle between active and idle. And second one, amount of time you spent in the idle state given that your first request came after you went to sleep. So that would be that second bigger cycle. So given all this, we can formulate the optimization problem that minimizes performance penalty under some energy constraint. You can also do it the other way around. And what's nice is we get globally optimal policy. It says here in seconds. It turns out we have reduced that to be less than a millisecond using some interesting techniques. They're actually hardware-based. So we can actually do it very fast. Yeah?
So just maybe I'm confused in the middle. So you started with showing us some traces of web traffic, I think, right?
Yeah, and actually have sensor traffic also.
So, and then you also talked earlier about video and audio and things. And the question I have is that if you're doing one specific, I mean, it sort of makes sense maybe for very generic design, but if you're thinking about anything like video and audio, why aren't you taking advantage of the periodicity of those things?
Exactly. So what I was mentioning, that's a great point. There are 2 different classes of applications that I can define. There's a class that tells me what its needs are, and audio and video would be that class, basically. I know that I need to deliver 30 milliseconds 1 frame. In case of a lot of other applications, I don't know. And this is where I use this.
Okay, so in that case, you actually have a separate mechanism to do this.
You can kind of think about it as a separate mechanism. Basically what it is if I have information, I use it. If I don't have the information, then I do the best that I can. And the best that I can is basically here. This policy guarantees to be optimal if my modeling is correct. Right? And modeling is reasonably close, because when we implemented this in real designs, we actually got pretty good results. So the way this ends up being implemented is you have some table that basically shows you if you've been idle for a certain amount of time, this is your probability of going into a given sleep state. Or this is your probability of going into a given active state. It's very, very simple to implement, almost no overhead. In fact, when I synthesized this into hardware, it took only a couple thousand gates to make it happen.
So you say modeling doesn't include exponential and Pareto both, right? Your modeling includes
both,
exponential at a certain
yes.
point.
And that's why actually we had to use this renewal model. Because if it was exponential only, you can use a normal Markov chain. The problem was, and this is something to really remember from my talk, it turns out if you use exponential model and implement it on real devices, you'll end up sometimes with worse energy consumption than you had without implementing anything. So we used exponential only, implemented it on a laptop through Windows operating system using ACPI. We controlled the hard disk. We had 20% increase in energy consumption. And the reason for that was that exponential model thinks that there is no history. It doesn't actually look at what happened before. It assumes that whatever is happening right now is all you need to know to make a decision. The problem is real systems don't work that way. So if your real system has very low overhead in terms of waking up and going to sleep, that's not a problem. But if it's something like a hard disk that takes about 2.5 times as much energy to wake up, then it's a big problem. Then you really want to know what's been happening in the past. And that's where this Pareto model makes a big difference. So it's really important, actually, to look at and measure how your system is behaving.
So why not have, in your system, have some mechanism of looking at whatever traffic the application is pushing down, and maybe putting some smarts there before you decide what sort of model you're going to start to apply to that particular application. So for example, if you were doing just web, which is kind of stateless almost, right? You could probably use exponential, I suspect.
Yeah, so that actually kind of happens naturally as part of this model, because anyway, we have to keep track of the traffic, as you said. We have to measure these inter-arrival times that come to us. So through that, you already have, in effect, characterization of what goes on. The last step on all this is doing scheduling. So if you look at very simple TDMA scheduling, we said, OK, let's fix the number of contenders to between 2 and 4. If you remember, wireless LAN showed a nice peak at about 3. So we figured if we keep it low, we'll get better throughput. And the idea, again, is applications send you data to our scheduler. Our scheduler estimates what's going on, figures out when it should forward the data to transport layer and to 802.11 MAC. And once it does that, so from this point on, everything behaves as advertised in literature. There's nothing new here. Really, the only big difference is when do we send this data in. So as you would expect, you see that number of collisions radically drops. You see a nice flat curve. Secondly, you see that your throughput automatically gets better. Thirdly, you can get a lot of sleep out of this thing. So your devices actually save a huge amount of power. The problem is TDMA has an issue with application level delay. So an obvious question is, can we use TDMA together with all the other fancy estimation techniques to adaptively actually assign who gets to go when? So applications that have very tight latency requirements at application level have a chance to meet those latency requirements. And others who don't care have a chance to communicate some, basically. How do we do that? In addition to that, the second issue that we're dealing with is, if you remember, I started the whole talk by showing you multiple levels in the network. And then I said we want to have quality of service, and we also want to have very low, very long battery lifetime. Well, to have long battery lifetime, you don't want your radios on. In fact, a good part of your network should be off. It shouldn't be talking. But to have good quality of service, you want your network on. So how do you do QoS-based routing in a network where most of the nodes are sleeping a lot of the time, and where who is asleep changes from slot to slot? In this particular case, we really need to look at policy-based routing that is actually tightly coupled with scheduling, and that is also distributed in nature. So that really motivates two topics that we're working on. One is QoS scheduling. That the goal is to design adaptive, distributed, and low-power QoS scheduling methodology. We want to understand and characterize incoming traffic. I showed you a small sample of that. I'll show you a little more in a little bit. We want to improve delay and throughput, reduce the power consumption. We've already done some simulations on NS2, done some measurements on X-scales with wireless LAN. Our next steps are going to be to actually deploy in Santa Margarita Reserve first, and then eventually throughout the network. Secondly, with QoS routing, we want to design an adaptive and low-power routing methodology. This methodology needs to actually work hand in hand with scheduler. It also needs to have a very good way to measure the quality of a route that doesn't cost much, that's cheap, that can happen quickly. So we did actually a little bit of measurements, again, using X-scales to evaluate and compare different ways of estimating the quality of a route. And we're right now in the middle of designing a router that would do a good job. So just to give you a quick sampling of results, Most of the results I'll show you were either measured on X scale or we actually did some simulations on NS2. So with X scale, we can do a lot of measurements, but not with many nodes, which is why we go to NS2 simulator. The applications we used are various sensor traffic that we collected from the network, so day-to-day operation. We also have some specialized traffic because this allowed us to really zero in on QoS and how well we can do for a specific application. So traffic characterization, I showed you this web trace. Here are two different sensor cluster head traces. And you can see very similar behavior. You see very heavy tail as soon as your idle times get longer. So if you sit at very short idle times, your exponential does really well. As soon as idle times get longer, you have a problem with exponential, which is why this combination of two distributions, I think, really meets the needs here. The implementation of scheduling and power management for video shows that if we stream 30 frames a second to a particular mobile terminal, we can get about 40% of power reduction. If we do 15 frames a second, we go up to about 65% of power reduction. And in fact, I showed you much earlier the effect of traffic conditions on 802.11. So we talked about light, heavy, and medium traffic, and I showed you that actually dose mode doesn't do so well. So what this compares is how 802.11 dose mode does versus how our methodology does in different traffic conditions. No traffic, light, medium, and heavy traffic. And you can see that we have pretty consistent savings and that we actually save, that we do really well in terms of quality of service. So in both cases, you have real-time video stream. The difference is that in this case, you save a lot of power. In this case, you don't save as much in heavier traffic conditions. Here is an example of audio. It's pretty much what you would expect. This is today's state of the art, where your 802.11 is always on. This is what could happen if you enabled dose mode and you had no traffic other than your audio. So this is the best case with 802.11 power management. And this is us right here. So we're doing some simple scheduling, basically. Yeah.
This is on old, like 4- and 5-year-old design references.
So this was actually done on an iPAC. So it was a strong arm with wireless LAN. Yeah. This is MP3 and email via Bluetooth. So what we're looking at here, because it was an iPAC, we're saying, OK, can we actually switch between 802.11 and Bluetooth on demand? And iPACs actually had both. So you could actually test it. What's interesting about Bluetooth is if you understand a little bit of implementation of that particular technology, it has a limitation of having only 7 nodes in the environment, in a piconet. And the only way you get around that is by releasing an address. And you release it by putting a device in park mode. So what we did, in effect, is we said, OK, because we can schedule, and we know what the demands of our particular application are, in this case MP3, we can use the park mode, and then we can even couple it with a special deep sleep mode that this particular chipset had. And what we do here, we accomplish both large power savings, but we also increase the number of clients we can support concurrently because we can release these addresses, essentially. So in terms of MP3, we increased by a factor of 2. In terms of email, by over 1,000.
These are watts in the vertical scale?
Yeah. Oh, another thing you should really notice, that was a good question on Bluetooth. So Bluetooth, if you look at the rating, it's much lower than 802.11. But in terms of energy efficiency, take 802.11 any day, because you can send stuff fast and then shut it off. That was a big lesson learned. On cluster head, we did some scheduling, and we said, OK, if we try to see what kind of modeling we can use from the point where our scheduler sends the data, so not data coming in to the buffer, but data going out of the buffer. Does it matter whether we use exponential, Pareto, as compared to the real data? And what's interesting is it turned out it doesn't matter a whole lot. What matters is on the incoming side, so when we decide how much data to send and when to go to sleep. On the outcoming, actually doesn't matter. And in fact, you can see that in terms of throughput, we see a pretty nice improvement in throughput. In terms of power, we see a huge decrease, pretty much irrespective of the type of model used. We compare here the real data to the exponential and Pareto models. And again, the problem comes up in terms of application level delay. And this is a problem that we're solving right now.
So these cluster heads are, who is scheduling these cluster heads?
cluster head actually so in current implementation, each cluster head has a distributed algorithm that basically decides who gets to go when. There is no need to communicate between cluster heads to make a decision. So what we actually we're using a time syncing, just one of the basic algorithms to keep the clock synced, right? But once the clocks are synced, the decision for every time slot is independent. So you don't have to actually, cluster head number 1 doesn't have to talk to cluster head number 2, 3, 4, and 5 to figure out whether it gets to go.
You don't worry about drips and things like that?
You have to resync periodically these clocks. But these are algorithms that are fairly well known, actually. They've been published. And it's not a time scale that's very tiny in our case. It's reasonably big time scales.
What is your slot size?
So slot size has varied between about 50 milliseconds to a couple hundred milliseconds. Obviously, from our perspective, big slot sizes for power are great, but big slot sizes in terms of delay are not so good. So there is a tension there, and we actually haven't figured out yet what is the best.
Big slot size.
Exactly.
And so, so you're assuming your queues are pretty full at that time, right?
Yeah.
Because otherwise, you would start losing energy if you were scheduling it and your queues are not full.
Yeah. Yeah.
How does this impact TCP throughput, if at all?
It actually makes it better. We've seen improvement in throughput because of scheduling. Most of our data, I would say, 80, 90% is UDP based. TCP has a bit of a problem with backoff, but the way we handle that is basically we put an interface above the TCP mechanism. So when TCP gets packets to send, it gets enough packets that it can send and receive within the time slot. So you don't really see this huge impact that you would otherwise.
I suspect you would actually see a lot of problem, right? Especially when you're doing multi-hop and you've got queuing delays at every node and they're doing distributed scheduling. So I would suspect that TCP is going to actually perform very badly.
So on a couple of hop level, we haven't seen a huge problem, primarily because of the scheduling that happens at the higher level. And I think it remains to be seen what happens at the more than couple of hop level. We haven't measured that. So
explore PCF at all, the point coordination function for
yeah, we've looked at that. Yeah, and so it works. You can use it for 802.11 specifically. The problem is, from our perspective, if you also want the node to sleep for a long time, then you don't actually gain quite as much. What we really wanted to be able to do is both. We wanted to get some quality of service, but we also wanted to have very long periods of time where you save power. And that you can accomplish if you have larger amounts of data sent less often, basically.
What about the .e things, right?
So that's a quality of service implementation. So I actually haven't used it on this network because the type of hardware that we have deployed, some of it supports it, but a lot of it doesn't. But I think it could certainly be used. I think that's somewhat orthogonal to what we did, because if you have 802.11e, you just enable it and use it. So we can propagate the priorities that we already know to the lower level. That's not a problem. I think our problem is more, what happens at this level above. Can we actually do some scheduling at that level? And you can see, in this quick summary, that we see improvements in throughput. They're about 20% approximately, 10 to 20%, with power consumption about 80% savings. And that's actually what we're targeting. If you remember, we wanted to have good quality of service, but we also wanted to have small and cheap nodes that are, easy to deploy. So that is what we're going to be getting with this kind of approach. On routing end, we've just started. One thing we do know is that hop counts do reasonably poorly as compared to the estimated transmission count. That actually does a lot better. We're currently looking at some other ways of estimating the quality of routes, specifically estimating them with the assumption that routes change continually, that good part of the network is not up. And that we actually haven't figured out. So I would love to hear from the audience any suggestions. So in conclusion, we are working on heterogeneous wireless sensor networks. We need good quality of service for some applications, not for all applications. We have best effort traffic for all the other data. The real key element is we want low power, as low power as possible. So as little communication, as much efficient processing locally, because a lot of times processing is cheaper and faster than communicating. To address that, we've proposed two joint approaches, scheduling coupled with QoS of error routing, and we're currently working on designing that. So that's pretty much it. For more information, you can see my website at UCSD. So I've included the URL. Thanks.
Thank you.
You guys, any questions?